Welcome back in part two of my talk on Hitchin representation in a lattice. So in part one, we defined Hitchin representation and we defined what a lattice is, and we asked when does a lattice contain the image of a Hitchin representation. So here I formulated the question, and there's one subtlety going on. I ask an easier question than what I asked before. Basically, I say, if you pick a lattice, can you find a surface for which there is a Hitchin representation in it? Probably the real question would be, if you pick a lattice, can you always find a Hitchin representation from a surface of genus 2? And here I'll say for a surface of sufficiently high genus. And I will give you a summary of known results and motivation for this question, and then I will go into my own results that have been to obtain so far. So first, when we consider Hitchin representation, Ho from Pi1s to, let's say, it lies in SL3Z, for example, which is a lattice in SL3R. If we have such a representation, then the image of rho is a subgroup that is isomorphic to Pi1s because rho is injective. That's a theorem I stated in the part one. So since we are talking about injective representation, the image will always be a surface group. And we are thus constructing surface groups of lattices. And those are in particular interest for various reasons. And one of the main reasons is that it is historically linked to topology conjectures. For example, in 2012, Markovich, in their really famous paper, they proved that all uniform lattices of SL2C contain a surface subgroup. So here, uniform means that the quotient is compact. We wanted to have finite volume, but we asked more than that. We asked that it is compact. And this is actually related to three-dimensional topology. Because it's a question about finding surfaces in three-dimensional manifolds, and especially totally geodesic surfaces. And it is linked to what is called the virtual Heiken conjecture, which I'll not explain now, just say that it has been proven to be true by Hegel, which used the results from Markovich. So after this paper, a lot of people try to push it further to prove the same results for other lattices, and they use the same technique. So all the results will be the next two results I will be giving use the same ideas of this paper that involve geometry and dynamics, cut your surface into pair of tens and do mixing and stuff. So first, in 2015, Armenstadt is able to generalize this to simple Lie groups of real rank 1. So for example, SL2C, but which are not isomorphic to SO2 and 1. Then she can prove the statement that all uniform lattices contain a surface subgroup. In the same year, Markovich are able to prove a similar result for lattices of SL2R times SL2R, and use this to deduce something called the Ehrenpreis Heron-Price conjecture, which is about comparing two Riemann surfaces. All right. More recently, Canlabouri and Moses in 2018 proved it for simple complex Lie groups, actually for much wider class, but which is they have a specific assumption. It's a bit hard to describe, but especially for simple complex Lie groups like SL and C. And they prove that all lattices contain all uniform lattices contain a surface subgroup. So all of these do not contain subgroups groups like SL and R, SP2 and R, or SO K plus 1K. Which are a family of groups which we call split, and those are the Lie groups that for which you can define what being a Hitchin representation means. So I gave you the definition for SLNR, but for SP2NR, it's a Hitchin representation in SLNR, which image lies in SP2NR. So same for SO K plus 1K. So there is a notion of Hitchin representation, and the question is, do lattices of those groups contain surface subgroups, and especially do they contain image of a Hitchin representation? So recently a proof have been announced from Armenstadt and a lot of collaborators and postdocs and people that work with her. They announced that they can prove that lattices of these groups contain uniform lattices contain a surface subgroup. But they also she specified that it's not the image of Hitchin representation. Those are not Hitchin representations. So Armenstadt ensures me that even though those results do not say that the image are very risky dense, they can be modified a bit to produce the risky dense representation. I'll define here what the risky dense mean. So Taiwanese, so okay, let's say I have a group which I'll call lambda. Okay, in G, we'll say that it is the risky dense if all polynomials in matrix entries, so element in G are considered as matrix entries, all polynomials that vanish on lambda vanish on G. So this says that from the point of view of polynomials, lambda and G cannot be distinguished. Like lambda is like dense in G, but for the polynomials. And the risky dense subgroups of lattices, they attracted a lot of attention recently because they are an example of what we call a thin subgroup. So if you take gamma in G a lattice, lambda, a subgroup of gamma, is thin if it is the risky dense in G. And of infinite index in gamma. So thin subgroups of lattices, they have been shown to satisfy, to be close enough to being a lattice so that they still satisfy the strong approximation theorem, and so can be used to prove existence of solution on for certain arithmetic equations. It has been developed by people like Sarnak, for example. That Sarnak is the one that introduced the notion of thin, the word thin here. And if we manage to construct Hitchin representation in lattices that are Zariski dense, then they will necessarily be thin because a surface subgroup is almost never of finite index in gamma, except if gamma is, when we look in SL3R or higher groups, it will always be of infinite index. So we will construct thin subgroups. So interested by this notion of thin subgroups, Longreed and Thistlethwaite worked a lot on, tried a lot to construct thin surface subgroups in lattices by being image of Hitchin representation. So they proved that all non-uniform lattices, so here they use arithmetic methods, and when you use arithmetic, non-uniform lattices are easier to handle, and we saw that when you use dynamics, uniform lattices are easier to handle. So they proved that all non-uniform lattices of SL3R contain the Zariski dense surface subgroup. So let me describe you up to finite index and conjugation. All non-uniform lattices of SL3R are either SL3D or SU I3 sigma Z square root of D, where D is in Z plus not a square. So this is an infinite family. And they showed that they all contain the Hitchin representation, which is Zariski dense, and they even give image of the generators. In 2018, Long and Thistlethwaite are able to do the same for SL4Z and SP4Z. The method is the same as Long with Thistlethwaite. It's always numerical methods. And it's quite different from what I do. And especially, I cannot obtain those results. And I explain you why those two results are in a sense harder to obtain. Okay, so now I can describe what I've been able to prove. So let's talk about SP2NR, the matrices that preserves anti-symmetric matrix. Okay, so those are the matrices that satisfy M transpose J, M is equal to J, where J transpose is equal to minus J. So J is anti-symmetric. Then we can show that all lattices of SP2NR except SP2NZ contain the image of the Zariski dense Hitchin representation. So I'm not saying that SP2NZ does not contain one. I'm just saying that I don't know. But for all the others, they contain the image of the Zariski dense Hitchin representation. So it's particularly interesting in the case of SP4Z. So let me draw H it S in SL4R. Okay. You basically have a subset which are representation with the image in SP4R. So not all Hitchin representation lie in SP4R, but some of them do, especially the friction locus. The friction locus is in this subset. So friction representation lie in SP4R. And here what I'm able to prove is that if you look for representation in SP4Z, what Long and Thistlethwaite tells us is that there is actually infinitely many representations in the Hitchin component that lie in SP4Z, but I'm able to prove that they do not lie in the friction locus. So there is no representation in SP4D in the function locus. I will describe you results for the exceptional group G2. So this is the centerless split form of Dinkin diagram G2. It correspondingly algebra is the split Lie algebra G2, but it's easier to describe. It's actually it's a subgroup of SL7R, and it is the automorphism group of an algebra, which is a noctonian algebra. So let me explain what a noctonian algebra is. So it is eight-dimensional unital. It means that there is a neutral element for the multiplication, non-associative algebra. It's eight-dimensional over R. It contains, sorry, there is a norm defined on it, which satisfies n of xy is equal to n of x times n of y. And we want that n as signature 3, 4. So there is actually only one octonian algebra like this. So this is what we call the split octonian algebra. And the automorphism group is G2. So there's something weird going on. How do we have that here? We have 8-dimensional, and here it's LCL7, because you can prove that that the center of O is 1-dimensional, and that G2 preserves this line, but also preserves its preserve the 7-dimensional space that is orthogonal to the center. So it preserves a 7-dimensional space, and if it preserves a 7-dimensional space, it can be written in terms of 7x7 matrices. Okay, so here I give you one way to define it, like it's by this cross product. So this is a cross product on R7. Actually, only R7 and R3 admits cross products. So the coefficients are a bit weird, but that's for a reason. That's because I want the tau n, as I defined it in the first talk, to preserve this cross product. Okay, so you take two 7-dimensional vectors and it gives you another one. I defined this symmetric matrix, 7x7 symmetric matrices. And then I can define G2 to be matrices in SL7R that both preserve G7 and the cross product. So if I take x and y, two vectors in R to the 7, and I do the cross product and I multiply by m, then it's the same as multiply m by x doing the cross product with my. Okay, so that's G2. And you can also recover the octonian algebra as a copy of R some direct sum with R7, and you ask the multiplication law will be, I take a T in R and V in R7, and I multiply with SW. It will be T equal to TS B transpose G7W. That's a number. And the vector part will be T times W plus SV plus V cross W. And you can also recover the norm, which take T in R and V in R7 to be T squared plus V transpose G7V. Okay, so when G2 is defined, we can like keep doing weird cross product and define in such a way the lattices of G2. Basically, lattices of G2 is, or like you take Z coefficients for matrices or Z square root of 2 or stuff like this. And the theorem is that all lattices of G2 contain the image of a Zariski dense Hitchin representation. So here I emphasize that it's about uniform or non-uniform. There is only one up to conjugation and finite index, only one non-uniform lattice in G2. And the way this is done is looking at the Hitchin component for SL7. Here we have the function locus. We pick gamma in G2 a lattice. Here we have representations that lie in G2. Not all of them do, but what we find is that when you have gamma, then you can find the cross will represent a representation in gamma. So you can find a representation in the function locus that lie in G2, and then you can deform it to find another one that also that lie in gamma, and you can deform it to find another one that still lie in gamma, but so that it became Zariski dense. Just to mention, like if you deform X a bit, it will either stay on the friction locus or become Zariski dense. But will no longer lie in gamma, since to lie in gamma you have to deform, like you cannot deform as small as you want. You have to deform at least a bit and be sure that all coefficients will fit with one another to lie in gamma again. This is because gamma is discrete. So for SLNR, the results are a bit sparse. It's I'm not going to describe them because that would require me to define notations to talk about each lattices, because I can prove for some of them that they contain Zariski dense Hitchin representation. I just want to emphasize one theorem. All non-uniform, so non-co-compact lattices of SL PR, where P is prime, contains a Zariski dense Hitchin representation. So this generalizes the case P equals 3 was done by Long, Reed, Cecil-Waits. And I mentioned it earlier, and basically I can prove SL5R, for example. One fact that is to understand how it's actually difficult to construct Hitchin representation in lattices of SLNR. And one fact that makes us understand that, for example, if you look only at functional representation, we can prove that SLNZ contains the image of a functional representation if and only if n is odd. That's why the odd case is always a bit easier for this question. So, for example, SL4Z does not contain any representation in the function locus, but contains a Hitchin representation by the result of long and Cecil weight. But you cannot, that means that you cannot construct a Hitchin representation in SL4Z by deforming one that will be in the function locus and would already be in SL4Z. All right. So finally, I want to look at the question we talked about. So we asked the following question: do all lattices of G contain the image of a Hitchin representation? So G here can be SLNR, can be G2, can be SP2NR, can be something like SO K+1K, the orthogonal group that preserves the bilinear form of signature K+1K. So in this question, well, depends. Sometimes we can answer, sometimes we cannot. But just want to emphasize on another question that seems interesting. The question should be not only if you contain a Hitchin representation, but do you contain one that is almost a fictional representation? So do all lattices of G contain the image of a Hitchin representation which is as close as possible from the function locus? In other terms, when you take a neighborhood of the function locus, can you always find a Hitchin representation that lies in a given lattice in this neighborhood? And that's a really interesting question because it's related to the proof of Kan-Markovich, Labourik, and Moses, and how they manage to construct. They always manage to construct representation that are as close as they want as a simple representation that is the analog of the function locus, but in their case. Thank you very much for attending those two talks. If you have any questions, feel free to ask. I'll be glad to answer them. Thank you.